Hey everyone, my name is Hemant Jain. And I'm a senior software engineer here at Cohere. My talk today is focused on efficiently serving fine-tuned large language models. And it's interesting because I want to focus on the fine-tuning part of things, not just the way to do fine-tuning and the new advances over there, but also how to really make the best of serving these models out there in production. All right. So to give you a brief introduction, Cohere is an organization startup focused on democratizing large language models. We want to power interactive chat, generate, or any kind of text-based experiences. Basically, give language to your technologies and integrate into all solutions around NLP and large language models. Make it easy for you to work through the stack, but also educate you about the best practices for all of these. I'm going to break the talk into three different sections. One is the why part, like why is there a necessity to look into fine tuning and optimize the way we do fine tuning. The how part as to how to go ahead and implement and make benefits from the ways I mentioned. And then I'm going to talk about like the serving part of things if we have some time at the ending. Why? So training from scratch is extremely expensive, specifically with this shortage of GPUs that we've seen lately. And as model sizes increase and the requirements for compute increases, it's going to become incredibly hard, not just from the compute point of things, but also from the data point of things. And you can, in fact, get away with actually taking these existing large language models and fine tuning them for your use case. The best way to actually understand if a model is good for your use case is actually get your hands on it and experiment with it. There are some concerns with latency and compute. We've seen that sometimes when you fine tune a smaller language model for your use case, you can actually get at par or slightly better performance in a much larger language model. And that means effectively your serving footprint, your costs, everything goes down, your latencies go down. And that's a huge asset to a lot of companies, specifically where like cost can be prohibitive for like parameters where there are 100 billion parameter models. Now is the part of understanding like why at all I care about it, even if cost is not a problem for me, right? I have like billions of dollars in my pocket, but what's still a concern? Well, not all use cases have language models that perform well with them. And not every language model performs well on all use cases. Specifically, ones that require higher quality performance, you want to tune them or like get something more out of that model for that specific use case. The objective of these baseline foundational models or like baseline models that we have in the industry is to just predict the next token. So they're trained for that. And some of people go a little further. They use like instruct style fine tuning to get it like to give better output to your questions. They have like humans preference based models that actually perform well for specific kind of chat based interactions with folks. But at the ending, none of these models are perfect today. So the solution can be a simple one. Can we just get away with prompt completion, right? Prompt engineering so that you get a better output. Well, that only gets you so far. And there are trade-offs. You have to give few short examples in your context, which means that even if you do, you're eating into that context length. So you are basically being limited by it. And even if context length isn't a problem, it's going to eat into the compute cost of your request each time a request is processed. It's insufficient for all of the complex tasks. So let's look at a more complicated, more interesting way to get our quality go better. There are two ways I'm going to categorize the fine tuning strategies. One is based on the data set and the model objective type, and the other one is the way the weights are being trained or updated. The first part, the data set and model objective type, is split into instruction style fine tuning and preference style fine tuning. These are the two popular approaches. The second part is you have this new strategy to do weight updates. Instead of updating the entire model, you can update like a section of it, but you can go even beyond that and do something called parameter efficient fine tuning, which I'll dive more into as we go down the road. One caution though, when you have to do fine tuning in general, is that you need a rich data set. If you just pump garbage into the model, you might actually negatively impact the quality of the model and it will have even worse output. So be careful the way you prepare your data sets and how you use them for fine tuning. With respect to instruction style fine tuning, I think the cool part about this is that it's very simple to understand. You have this prompt, which is like the input going to the model. You have this completion, which is the output coming from the model. And you use this to kind of nudge it towards the kind of generations you want. The good part about this is the fact that you, without doing prompt engineering, you can actually have like zero shot good performance on certain tasks, and it gets you to a good degree over there. For some use cases, this is well and good. The disadvantage comes from the fact that this is a little time consuming to prepare the data set. Can you imagine like preparing thousands or 2,000s of variable pairs of inputs that have prompts in completion for your use case? It's definitely time consuming. The more popular approach and the one that's getting a lot of attention lately, a lot of buzz around, is this preference style of fine tuning, where you actually have these models have input in the form of not just like a prompting completion, but there's additional signals around like some feedback or some external signals that give the model a nudge in the direction of preference. This is really cool because you have a model or a human evaluating the output of an existing model and giving it an explanation or a rating or some kind of feedback on the output, and not just like it having like this is the perfect output, just try to mimic it, right? The cool part is that it's fairly cheap to create this data set, and you can actually go ahead and create a fairly large data set without much time or money invested into it. The disadvantage is the fact that this might not fit in into all kinds of fine-tuning strategies or use cases that you have. The next type I want to talk about is like the type of like distributing the fine-tuning strategies in terms of like the weight updates. So you have the baseline model, right? This entire Llama model, or like this Chat GPT model, or this Cohere command model, right? You can update the existing weights of these models. You can take that model and decide you want to update the last n layers, like maybe last 20 layers or something, and just fine tune that. So you can do like full, quarter, or half, whatever you want. The problem though is for doing like full model or even like a quarter model fine tuning, the computational requirements are fairly high. The memory requirements are fairly high. And you usually need a large enough data set for you to benefit from using this full model fine tuning approach. The resulting checkpoints produced are fairly large. If you do like baseline fine tuning and you fine tune maybe a 100 billion parameter model, that resulting checkpoint is going to be 100 billion parameters. So that complicates the way you can deliver and work with these kind of fine tunes. The good part is that it generalizes well to data from new domains. So if you want to tailor your model to an entirely new domain, for example, the healthcare domain that the model has never seen data of, it's generally going to perform better for that domain. The second style, which again I find really exciting, and I think this has huge potential, is parameter efficient fine tuning. This is not just like reduced size of model checkpoints, but it's slightly smaller memory requirements and it's much cheaper to do. It's generally a little faster to do as well. You don't modify the existing baseline weights. This is the form of additive fine tuning where you add additional weights to the model. And depending on how you add weights to the model, there's a different strategy to do that. But the resulting checkpoints can be from a few megabytes to like hundreds of megabytes. And that's like 100x, 1000x, 10,000x smaller than the entire model. The cool part about this is that it unlocks this really cool way of serving multiple fine tunes together, which I'll dive into later on. But this is just the two ways of fine tuning. Let's dive a little bit deeper into parameter efficient fine tuning, because this is where I feel like the most cost savings and the industry is kind of heading towards in terms of the more efficient way to get fine tuning out there. There are some approaches called LoRa, ADA LoRa, and IA3 or TFU that are popular, but there are other approaches as well. I'm just going to talk about these right now because they're more popular and it's been a while they've been out there. So, like I said, this additive method for fine tuning, right? So, you add additional weights generally around the attention layers of these large language models. And when you add it to the attention layers of these large language models, you get the ability to update a very small subset of weights that are in addition to the regular model. And that ends up being used during inference time. So low rank adaptation takes advantage of the fact that when you multiply two different matrices that are small, you can actually get a much more larger resultant matrix that can be added to your additional original baseline matrix and give updates around that. The advantage of this is that it gives you a little bit of a wiggle room of like the kind of size of the weights that you're updating, which may allow you to capture a little more complex patterns in the data. Ada LoRa, and you might have also heard of Q LoRa. There are improvements to the LoRa approach, which try to reduce the overhead. They try to use quantization to accelerate the process and use additional improvements around that. But I want to talk specifically a little more depth about TFU, which is a slightly newer approach. It's it was supposed to be an improvement of the LoRa approach. It's not going to give you the flexibility of changing the size or the amount of weights being updated, but it's producing a much smaller fine-tuned checkpoint. Instead of like it being 0.1% of the model weights, it's 0.01% of the model weights. And that order of magnitude can be a huge difference when it comes to not just overhead, it adds during the fine-tuning approach, which in the case of TFU, you can actually combine them into the baseline model weights. And the overhead can be as less as 1% or so, but it unlocks some additional really cool enhancements that we've at Cohere been experimenting with and used out. So this is a visual that kind of explains low rank adaptation versus TFU. In the case of low rank adaptation, as you see, there are like two matrices that are being multiplied. And then in turn, like these are added to the baseline or pre-trained set of weights to get you the resultant new matrix to be used for computation. In the case of TFU, there are three different places where these weights are injected. If you have the diagram over there, you see that there's K, V, and FF. So in the FFN layer, you can actually do like an element-wise operation with the one-dimensional matrix and update the existing set of weights and repeat that process for both the K and the V. The cool part about this is that the additional set of weights added are architecture dependent and limited, but they're much smaller in the case of like almost 10,000 times smaller for some kinds of models. The benefits of this are really coming from the fact that you can do some cool serving or like even fine tuning optimizations because of doing parameter efficient fine tuning. And there have been some advancements to low rank adaptation or LoRa. Like I mentioned, there's ADA LoRa, Q LoRa, and the open source community and the research community have been iterating very fast on this. And it's been impressive to see the work they pump out. In terms of the tricks you can perform, Q LoRa covers some parts of this and ADA LoRa as well, where you can actually offload some of the weights to the CPU memory instead of the GPU host memory and the device memory. And you can actually reduce the footprint of GPU or memory required on the GPU to perform fine tuning, which allows you to fine tune much larger models, albeit a little slower, and get away with using smaller, cheaper hardware to perform your fine tuning, making it more accessible to a bunch of people. The other idea is to basically not do parameter efficient fine tuning for all the layers, but restrict it to certain sets of layers or certain sets of operations. Generally, all of this is still around the attention layer of the model. The next one is quantizing these model weights. So when you are doing parameter efficient fine tuning, it's good to quantize the baseline set of weights and use that further reduce the memory footprint, because a large chunk of these come from the baseline set of weights. There is a lower bound, though, of the memory footprint to be used when you're doing parameter efficient fine tuning. And that comes from the fact that when you're performing these operations and computations for fine tuning, you still require to do the back propagation across all of the baseline set of weights. So even though you're updating only 2 megabytes of weights, your footprint for all these activations and computations for back propagation, they might still be fairly large. You can actually do something cool with the TFU set of weights. Like I mentioned, it's this element-wise operation. So you can actually just update that existing model with the TFU set of weights and produce an existing new model where it's really just the same baseline model. There's no architectural difference. There's no additive layers. It's just that the TFU was squashed into the existing model itself. And in that case, you don't really have any overhead of inference, which is nice. However, you can actually stack multiple of these parameter efficient models. And we've done this for the TFU or IA3 approach. And I'm sure it's possible for the LoRa approach as well. But you then do conditional computation. So your GPU memory footprint increases by the proportion of the model weights that you're adding, and the number of them you keep adding to it. But because you're doing conditional computation and doing this inference, you can actually serve multiple fine tunes concurrently on the same resource or the same hardware with an overhead of under 5%, which I think is phenomenal. Like this allows you to do so much. You can combine like 50, 100,000, 10,000 fine tunes into the same hardware and only serve the ones that are required from it. You can do things like caching and a bunch of other advancements to actually do that and further increase the amount of things fine tunes you can serve on that same hardware. But the other thing that you can look at is that I don't want to cache, I don't want to do all of this. I'm okay with that limited overhead, but I want flexibility. In that case, you can do something called weight streaming, where you stream in the additional set of fine-tuned weights, which is, like I said, very small, right? Like it's 2, 3, or 5 or 10 megabytes, which is much smaller than the actual model weights. And if you're okay with that overhead, you can actually basically update these model weights on the fly and do inference on the fly. So you have a very flexible architecture, and it depends the kind of use case you're kind of catering to. The cool part, as I mentioned, right, is the fact that you can really, really take advantages of this by allowing you to do batched inference across multiple of these fine tunes together. Thereby, if you have traffic for 50, 60 users coming to 50, 60 different fine tunes, you can actually just parallelize and take advantage of batching across all of these different users. Thereby, you increasing GPU utilization and significantly reducing the cost. I do want to warn about fine tuning in general, or like whenever you're training a model in general. Benchmarks are not a proxy for model quality. They're not a holistic evaluation of the quality of the model for your specific use case. However, if you are on a tight budget, you might want to pick a good benchmark to evaluate these models on, or a task that mimics as close to the task that you have as possible. There's Big Bench Hard and there's MMLU, which are really good benchmarks to uh, assess your model quality on after fine tuning. But again, these will not assess it specific to your use case. So the best way to do this, if you have a good enough budget, is to do human evaluations. Or I think asterisks, you can have a model evaluate your output. And this automated way of like evaluating using an LLM to evaluate an LLM might introduce some bias, but in some ways you can get away with significantly reduced cost and allow you to iterate faster during the fine tuning process, where you produce like maybe 10 models, evaluate them, and pick out like the best two, then have a human evaluate it post that. Do be careful to vet your data, not just like the format or the way it's prepared so that the model achieves better quality, but keep in mind where your data comes from when you fine tune these models. And be aware of the fact that when you do fine tune these models, if your data is not of the same quality, or if you're using improperly collected data or improperly formatted data, you can actually reduce model quality, and that's a real concern. Um, no one size fits all. There are some cases where parameter efficient fine tuning doesn't work for you. There are some cases where vanilla fine tuning might not work for you. Some cases where you might want to not do stacked fine tuning or all of these serving optimizations. You just want something clean vanilla that works with existing frameworks over there. Pick the one that works best for your use case. Um, and keep in mind, there's a trade-off between the overhead and quality, right? So as you keep using vanilla fine tunes, or if you keep using like large LoRa weights, you might capture better output or like better model the data, but you're gonna suffer in terms of the overhead of computation over there. And while I have a couple of minutes, I want to dive a little into the serving set of things. I'm going to jump past a couple of this and talk a little bit about the problem of long generations. Keep in mind when you're doing these generations, some of these serving benefits work across not just fine tunes, but baseline models as well. The time to output each token can be very large, specifically for these larger parameter models. They can go up to 20 or 30 milliseconds per token. Think of like 200 tokens is around like 7 to 10 sentences. If you're waiting 5 seconds to get your output, you're going to use the user's attention, and you're going to not be a viable use case, a viable thing to use for multiple online use cases. Use streaming to make benefit of this. And apart from streaming, to reduce the perceived latency of the user, do better batching. So in computer science in general, and in specifically machine learning, you take advantage of batch processing and the fact that parallel computation of these GPUs are optimized for larger matrix multiplications, and you get benefits from them. So a batch size of 10 is obviously not 10 times slower than a batch size of 1. You're coming to this concern now where batches might end differently at different times. You have this variability around sequence lengths and a bunch of other things. And you'll see like these batches end at different times. So there's those white boxes that indicate wasted compute. This basically describes a problem where the completion length, the output from the model, is variable and in many cases unknown if your model automatically decides to end generating based on end of sequence token. This will result in underutilization of your hardware. In terms of the way to solve this problem, there was this blog article, and there's a open source repository called VLLM that talks about continuous batching and how you can actually like squeeze in these gaps, other generations, and concurrently do this. Now that image on the right shows that you can actually do much more compute at the same time from the same hardware. There's a slight trade-off in terms of latency, but it actually does improve your median latency overall, and it gives you significantly higher throughput. Some of these might not be supported in all frameworks, but it's a huge asset if you have it. How do you really scale to production workloads? You did continuous batching, you did fine tuning, and a bunch of things, but now you're having the problem of multiple replicas of these models and load balancing across it and scheduling across it. Round robin will not work because the output time, or like the time to completion or ending of a batch, isn't the same across all of these replicas. So you can't really schedule just based on that. You need some form of distributed queue that is aware of the length of the completions and the batch sizes, and that schedules based on that. Not just controlling a more larger batch size for you to get to that, but so on. In summary, though, I do want to say that there are several ways to improve the overall performance of your large language model that isn't very, very deeply machine learning specific, but system specific. And I've broken these into the summary of like using KAV caches to basically uh, reduce computation during the hidden state operations and improve your runtime over there. There is batching in general to improve throughput. You can go a step further and implement continuous batching and streaming to further improve your utilization of your GPUs. You can use distributed queues to handle doing this across multiple instances of your model. And you can use dynamic batching across these models to basically adjust the max batch size and the context length based on the memory requirements and based on your SLAs for latency. And that is basically the recipe of efficiently serving fine tunes of large language models in production. Thank you. Feel free to join our Discord. The link is right there.